Hello, I'm Anurag, Daram, a PhD student in the Neuromorphic AI lab at UTSA. So today I'll be presenting my work, Neuron State Dependent Mechanisms for Efficient Continual Learning. Is this the controller? Yeah. Yeah. Oh, this just went. Okay. Okay, so this is the outline of my presentation. I will start with the background about continual learning and the challenges that pertain to continual learning. Then this will be followed by the methods to address continual learning. What are the limitations of the existing methods and what is the proposed solution? And that will be followed by the neo architecture as well as what is the intuition behind the proposed mechanism. And this will be followed by the experimental setup, results, and analysis of neo on some image classification datasets. So, yeah. So what is continual learning? Continual learning AI, even though it's an overarching definition, but a continual learning AI is a system that should be able to rapidly adapt to new, new conditions or tasks without forgetting previous knowledge. And at the same time, it should be able to continuously improve its performances on both the previously seen as well as the novel tasks. And at the same time, it also has to be able to operate at varying timescales and frequencies, wherein the task could vary based on their size or the length of the task or the frequency at which a task is exposed. Even as you can see in the diagram or the plot there, even though it's an overarching definition, that is what continual learning, that is what we look towards a lifelong or a continual learning system. However, continual learning also brings some challenges along with it. Why is this like? Oh, move ahead. This is not moving ahead. Yeah. So it brings in new challenges with it. First challenge is catastrophic forgetting of previously learned tasks. So as you can see in this GIF, like the model first learned how to park. And then in the next task, which it learned sequentially, it started learning how to merge. And then as soon as it learned the next task, you can see that it's not able to park properly. And then afterwards, it learned another task, which was passing or overtaking other cars. And as you can see, it fails miserably. And the other problem is unable to rapidly adapt to changing data distributions and tasks. So in this case, the robot is able to first learn how to walk indoors, then walk outdoors, and then it encounters an unexpected situation wherein oil is spilled and then it will just fail and it will fall. However, researchers have worked hard towards developing different continual learning methods, and most of these methods, okay, yeah, and most of these methods, wait a minute. Yeah, and most of these methods can be classified into three different approaches. Namely, first is regularization. In these kind of approaches, okay, yeah, in these kind of approaches, we first identify the important parameters, which can be weights or synapses, and then the changes to these important parameters are heavily penalized. So what this ensures is that it preserves the previously learned knowledge or information. And the next approach is replay based. In these kind of approaches, the previously learned experiences or samples are either stored in a memory buffer or generated using a generative model. And then these experiences are interleaved while training on the current task. So what this enables is, like, the model is exposed to what the previously learned experiences while learning newer tasks, and this enables it to generalize across all the tasks. And the third approach is dynamic architectures, in which, in order to accommodate new knowledge, we either add more capacity to the model by either adding neurons or layers or new synapses, or we can make some structural modifications to the network wherein we can sparsify or gate some sections of the network based on what kind of task we are learning. And in this work, I'll be focusing on the regularization-based approach and how, and despite this, like all these approaches are generally evaluated in 3 different scenarios for continual learning. So these are the evaluation scenarios, and the evaluation scenarios are basically determined based on if the identity of the task is provided or else how the network is set up. So the first scenario is task incremental learning. So in this scenario, the model is given the task identity, or it knows when the task is shifting, and the policies to either decide the important parameters or replay the previous samples or maybe add new neurons or synapses are done at the task boundaries. And then a much challenging scenario is the domain incremental learning scenario, in which the task identity is not provided to the model. However, it has to just determine which class the input belongs to. So basically, like it does not care about what is the exact identity of the input sample which it's getting. So for example, it has to just be able to classify whether it's an animal or a vehicle. If we give it a panda or a fox as an input, it just has to classify that it's an animal. And suppose if it's given a ship or an airplane, it should just be able to classify it as a vehicle. And then a much challenging scenario is the class incremental learning scenario. In this, the task identity is unknown, and at the same time, the model also has to infer the class identity. So it has to determine, okay, given a sample, is it a panda? Is it a bus? Is it a ship? Is it a dog? So these are the 3 different scenarios in which generally continual learning models are evaluated. And however, these scenarios also bring in some limitations. So yeah, so the continual learning system, the main goal of a continual learning system is to capture the real world deployment for these models. And in real world, we cannot expect any task boundary or a test time oracle to give the network the task identity or tell it like when the task is changing or shifting, right? So, and especially when we're targeting low end systems, there are much more constraints in terms of resource, energy, memory capacity. And as you can look at the right in the table, you can see that these are all the different continual learning models. They're color coded based on which approach they belong to. And these models every model is associated with a memory overhead. And this becomes significant when we are looking towards edge-based applications. And among these, in general, regularization approaches usually have the least memory and computational cost because we don't have to store a lot of previously learned samples. And at the same time, we are not growing the network. They usually operate within a fixed capacity. And however, there's a catch here. Most of these methods do not operate in task agnostic scenarios. And the memory overhead cost is also dependent on the type of importance measurement technique which is being used for the regularization method. So coming to importance measurement techniques, there are 3 different ways we can measure the importance in regularized space approaches. One is weight importance using weight statistics, in which each synapse or weight gets an additional importance parameter, and that parameter, that is the additional overhead for the network. And that parameter is determined either by looking at how the weights are changing or moving based on the task shift, or based on how the movement and gradients is observed, or the loss function is observed when the task shift occurs. And the next part is the neuron importance using weight statistics. In this scenario, we have one importance measure for each neuron. So we are trying to identify an important neuron, and that importance metric or importance parameter will be given to all its presynaptic weights. And this importance parameter is computed by usually measuring the variability in the incoming weights that the neuron is receiving. And the third part is neuron importance using neuronal statistics. In this case, we measure the neuron importance using the firing activity or the firing pattern of the neuron, or the activity trace of the neuron. And there's a trend. In general, weight importance-based approaches are the most common, and they demonstrate superior performance in both task-aware and task-agnostic scenarios. Neuron importance-based approaches, on the other hand, they are able to achieve comparable performance in task-aware scenarios and are more memory efficient, but they don't operate well in task-agnostic scenarios at all. So there's a need for neuron importance-based approach that can achieve comparable performance in task-agnostic scenarios. So what is the solution for it? I propose a neuron state-based importance mechanism with selective learning rules for continual learning. So in this context, having neuron state-based importance reduces the additional overhead for storing all the per synapse regularization parameters, and having the selective learning rules based on the neuron it's connecting enables to alleviate catastrophic forgetting. So let's dive into what the model is. So in Neo, I encode the concept of states into neurons. It's a very simple concept. A neuron can be in either of these three states, that is plastic, unimportant, or important. For unimportant new state, we assume that we can assume that they will be the neurons which will be probably be learning future tasks. And then for plastic neuron, that's a neuron which is learning the current task and will transition either to unimportant or the important state. And for the important neuron, that's a neuron which is basically preserving the previous knowledge or protecting the previous knowledge. So this is how the state transition diagram for this looks like. So a plastic neuron, if it has a moderate activity trace, it will stay in plastic state. If it has a high activity trace, it will move to important state. And once it goes to important, it's a terminal state, it will stay right there because we don't want it to move back because it leads to unstable dynamics and the model won't learn or preserve anything. However, if the plastic neuron has low activity trace, it will go to an unimportant state. And based on its activity trace, it can either jump back to plastic or it will stay in the unimportant state. So how am I doing this? How am I giving a state to a neuron, right? So the first part is like, I use the concept of using activity traces to decide which state a neuron will lie in. So I use a cumulative moving average for computing the activity trace or keeping track of the trace of activity of a particular neuron. And then during a state update interval, a transition condition is dependent based on two different thresholds, upward threshold and the lower threshold. If the activity trace is greater than upward threshold, it will be in important. If it's lower than the lower threshold, it will be in unimportant state. If it's somewhere in between, it will be in the plastic state. So now the next question arises is like, are activations enough, or do activations hold the important information necessary to preserve the knowledge for the task? So I did a very simple experiment in which we wanted to see if activation has a correlation with the importance to the task. So in this case, it trained a MLP on the MNIST data set. It has two hidden layers, and then selected after it has been trained, I selected the top n% activations, its average is top n%, and then remove those n% activations and reinitialize the weights and check how it affects the performance or impacts the performance. And as you can see, as soon as we remove the top n% or top 20%, there's a significant drop in performance. Whereas if we drop the bottom 20% and reinitialize that, there's a very low drop in the performance. In addition to this, now I also wanted to see how does the distribution of the activations lie, right? So I did one more experiment in which we took the per unit average activation of 1,000 samples of MNIST dataset. And we can see that it's a very skewed distribution in which only few neurons are highly active. And one way to like preserve this knowledge is basically we can preserve or protect these few units and then reserve the other nodes for basically learning the future tasks. And one more question that arises, since this is a trained network, right? Will this skewness remain even during training? So I checked for that also, and we can see that even for 10 networks, the skewness remains high even through the training phase. So this shows that we can use these activations as a mechanism to compute the importance. And now let's come to how the learning procedure works. So at the initialization phase, all the neurons will be in plastic state. And then at a state update interval tau, we will identify what are the important and the unimportant neurons. Then at the next step, the incoming weights to the important neurons are either regularized or decayed, a slow decay process based on where the weight is coming from or where the synapse is coming from. And the outgoing weights from the neurons which have been deemed unimportant are rescaled or they undergo a fast decay process. So now we have 9 different types of connectivity or mappings for the 3 different states, right? Among these, I selected like 5 different connection types which are important and decided to have a different learning mechanism to either protect that knowledge or make them plastic for learning new tasks. So if it's a weight connecting an important node to another important node, then we'll have to regularize the connection. If it's from a plastic to an important node, it undergoes a slow decay process. If it's an unimportant to important node, it undergoes a faster decay process wherein we want to remove the dependency of the unimportant node for the important node. And all the other outgoing connections from unimportant nodes, we can try 3 to 4 different topologies. We can either rescale those connections, either reinitialize the connections, keep them unchanged, basically let them learn using SGD as normal, or we can even prune them. And for the others, there's no additional rule which is added to it. So let's look at how I'm doing it. For the first important to important neuron, I just regularize the synapses based on the strength of the activity trace which the presynaptic connection has. So if the presynaptic node has a very high activity trace, any changes to that weight will be heavily penalized. And then for a plastic to important neuron, it undergoes a slow decay process. So this equation has 2 different terms. One is a decay term and then other is a magnitude penalty. The beta represents the decay rate and the beta dash represents the scaling factor. So what this decay does is, like at the time of state update interval or transition, we identify, okay, this weight, if it's moving away from what value it was, we try to pull it back to the actual value it was there. And suppose if the connection is coming from a much active node and the weight value is very high, it receives an additional magnitude penalty such that it does not deviate a lot from where it was initially during the state update transition. And then similarly for unimportant to important, it undergoes a fast decay process. So here the decay rate is slower, but here the beta value becomes a function of the average layer activity and the synaptic activity trace of my presynaptic neuron or the unimportant neuron. And that trace determines like how fast I want to decay that to a smaller value. So I could select a minimum value, or else I can decay it to the reference value it was during the state update transition. Yeah, and then the final one is unimportant to plastic or unimportant neuron, the other outgoing bits. So we can either rescale, reinitialize, or don't change them. So rescaling, what rescaling does is, what reinitialization, let's start with first reinitialize. What reinitialization does is, it kind of gives those weights, gives the chance of getting that node to learn for the future task, basically increasing the plasticity. However, what rescaling does is, if the weights are very low for that particular node, those low valued weights are slightly upscaled so that they can learn for the future tasks. So now let's come to the experimental setup and analysis. So I analyzed NEO in both task and domain incremental learning scenarios. So in both task aware as well as task agnostic scenarios. And the setup was, I used split MNIST and split fashion MNIST benchmark and split Cypher 10. For split MNIST and fashion MNIST, they're like just a simple MLP with 400 neurons per hidden layer and 2 neuron output layer in case of domain IL and 2 neurons per each task in the case of task IL. For the split Cypher 10, I used a pre-trained ResNet 18 autoencoder, and the latent space again goes back to the similar setup for the previous one. For the baseline model, I just used a network trained using SGD with a learning rate of 0.001 and trained for 5 epochs. And the state update interval, the tau value is set to 2500 in this case. And in task aware, the state update interval happens at the task boundary since the model is aware of the task. identity. So now, as you can see for the task IL results, like we can see that the neuron regularization as well as weight regularization based approach all are able to achieve good accuracy, and the neuron based regularization approaches are able to achieve comparable or better performance in the task IL scenario. So that's a good result for task aware. But when you switch to domain IL results, domain IL scenarios, as you can see for fashion MNIST, you can see the weight regularization approaches are performing way better than the neuron-based regularization approaches. And you can see that NEO instead performs much more better, much more performs much better than the other weight neuron regularization approaches, and has a minimal memory overhead. As you can see, like the neuron regularization have very less overhead, but then they're not able to perform well. So that is something which NEO is able to address. And let's see, like I was talking about the different learning mechanisms which you could have for the unimportant, for the connections, outgoing connections from unimportant nodes, right? So I wanted to see how that affects. So what are the 4 different methods we have tried? One is pruning, either rescaling, either keeping them unchanged, or reinitializing those weights. Sorry. So what we can see is that strength-based rescaling works better in task-agnostic scenarios. So what it does is, like if we reinitialize at every state update interval, it keeps on adding. It's like we are making the network plastic even while learning a particular task multiple times. And that leads to mirrored activations wherein there will be neurons which will be firing with the same activity pattern. And that might be the reason it leads to a slighter drop in performance. Whereas rescaling, wherein we are slowly upscaling those values, it allows the model to learn slowly and adjust its weights accordingly. Whereas in task IL scenario, if you are reinitializing the weights at the task boundary, so that is the best time to reinitialize the weights. So what happens if at the task boundary, if we are reinitializing the weight, we are incorporating new plasticity or enabling the network to be more plastic while learning newer tasks. So that boosts the performance in the case of task IL scenario. So this was one difference which was noted. And then the next part is I spoke about state update interval a lot, but how do we model the state update interval? So I tried to see how it affects the performance in both task IL or domain IL scenarios. So in this plot, on the y-axis is the mean accuracy. On the x-axis represents the different state update interval. What is the mean accuracy I got for different state update intervals? What can be noted is that if there's a lower state update interval, there are very faster transitions, or the rate of transition would be higher, and that would lead to unstable dynamics wherein it could either make the network more stable such that it won't be able to learn, it will be able to preserve the previous task knowledge, but won't be able to learn the later tasks. Whereas a higher state update interval leads to a much better or a much smoother, much better performance or much smoother transition in which, okay, the neurons can transition maybe 3 to 4 times in one task. And as you can see, like in this one, it shows how many neurons transitioned from plastic to important and unimportant state after learning the first and the last task. So if you can see, if it's a lower state update interval, you can see in the first task itself, there are so many transitions which we don't want, because then as we saw in the previous distribution, there are very few active neurons which can hold most of the knowledge. So we ideally want a behavior which is closer to like when the state update interval is 2500 or 4000, wherein the number of transitions in the first task itself is lower, and it's more balanced between the first and the last task. So lower update intervals leads to faster transition. Therefore, it basically affects the plasticity of the network for a learning later tasks. So what are I conclude by saying that like NEO is able to demonstrate near state-of-the-art performance on both domain IL and task IL scenarios with minimal memory overhead. And this is achieved by coupling activity-dependent neuronal state-based importance with some selective learning mechanism. In addition to this, we also observe the role of neuronal activations in the context of continual learning and how they are important by learning a task. Through ablation studies, we are also able to demonstrate how different learning mechanisms impact the performance of the model in task-aware and task-agnostic scenarios. So, for instance, rescaling in task-agnostic scenarios avoids mirror activations and is better strategy, whereas in a task-aware scenario, you could just go for reinitializing the synapses. And the future work will explore combining NEO with other activity-dependent mechanisms such as neuromodulation to enable, or some gated attention mechanisms to enable few-shot learning. And another extension would be to incorporate a context detection module to dynamically determine the state update interval. So if it understands that there's a shift in context, it will just change the states during that particular shift. These are references. And thank you. Any questions?